form of puzzles, and one of the puzzles is related to graph theory. So from that, Arnab will take over graph theory. So he'll go through the terminology, basic terminology and stuff. So yeah, coming to our first puzzle. So yeah, it goes like this. There are 100 people in an island, and right, so it's ruled by a mad dictator. And the thing is, so there are 100 people in this island, and anyone can ask to leave at any point of time. Okay, not any point of time. Let's say at any night at 12 a.m. you can go and ask to leave. And so if your eyes are green color, then they'll let you go. Otherwise, they'll toss you into a volcano. Right. So the catch is you don't know what your eye color is. So if you know your eye color is green, then obviously you can. Every green-eyed guy will ask to leave, and they'll be set free. But the point, yeah, and the thing is, all the 100 people have green eyes, so that's good. But everyone does not know their eye color because everyone is born and brought up in this island, and no one knows the color of their own eyes. And there are no reflecting surfaces, and water is opaque, so you cannot use water and see your eye color. And people are forbidden to talk about their eye color. So basically there is no way you can know your own eye color. So that's the point. So you are a human rights activist, and one day the dictator is forced to free all these people, right? So he does not like to make your job very easy. So he has some conditions. So he says you may only make one statement, and you cannot tell them any new information. You can go and announce something, and it should eventually lead all of them to know that their eye color is green. Right, so that's the question. So can you guess what you have to say them
Mm,
so that
I think I know the answer.
yeah, okay, so
I've seen this before. It's on TEDx, right?
yes, it's a famous puzzle, right? But that's not the answer is not the point.
Mm-hmm.
Right, so okay, can someone tell your reasoning and why this works?
Yes, I can say.
Yeah.
Okay, suppose I'm taking a small group. Okay, suppose there are two people.
Yes.
So both of them have green eyes. So, but nobody knows. I mean, none of them knows about their own eye colors. Okay. So the first day, the both will wait since they are seeing the other one is green eyed, but they don't know about themselves. But the next, but nobody will leave because they are not sure about their own color. But as soon as the day one passes, now then the suppose I'm thinking about only one person, so the one person will think that the other person has green eyes, but why didn't he leave? So it means that I also have green eye and he was waiting for me to leave, and he does not know about his own eye color, which means that I have green eye. Otherwise he would have lived saying that one of them is green colored, so he should leave, right? I mean, if suppose there are two-person A and B.
Yeah. So yeah, it's clear. So if there are, so you solve the puzzle for two people. If there are two people, and you say at least one of you have the green eyes, then uh, it's clear that if only out of two people, if only one has green eye, then he'll immediately leave because he'll see that the other person does not have green eye. But if both of them have green eyes, it will take an extra day to come to the conclusion that okay, I am also like you will say green eye guy, but he did not leave, which wouldn't have happened if you were a non-green eye guy. So both of them have to be green, and this kind of inductive argument works out. You take three people, and you use the reasoning for 2 people and then you say, okay, they'll 3 leave it the 3rd day. Okay, the solution is fine. So that is a solution. The thing is, if you say this statement, strangely, all of them will leave on the 100th day, right? You can follow the argument by this, like consider 1 guy, 2 guy, 3 guy, 4 guy, and you'll realize you can generalize it. But the point is, my question is, see, everyone can see 99 green eyes, right? Beforehand, even before this uh, announcement. So it is, this knowledge is already known, right? At least one of you have green eyes is already known to everyone. How come when a new person comes and announces it, why did it make a difference? Do you see the real question? I know that you have seen this video. I know that you know the answer, but I'm going deeper. So do you understand the question? It's kind of obvious even before she's telling, right, that there is at least one green-eyed guy, because everyone says 99 green-eyed guys. It's kind of clear that, okay, there is at least one green-eyed guy. But how did it make a difference when she announced something? So she's actually giving some more information, but what is it? Actually, she violated this rule. You cannot tell them any new information. Not exactly, but kind of, it's, yeah, it's something complicated. But yeah, can you figure it out? What made the difference?
Something new is there in the system, but
What?
something new information is there in the system, but
Yeah, what is it? How did it make a difference that the fact that, I mean, whatever statement she's making and what they already know, how did it make them, realize that their own eye color is green? And why didn't,
I mean, you
why
are
can't,
asking.
yeah.
I mean, you are asking what if it does not announce it? Then what will happen?
Yeah, I mean, the question is, so she's telling some statement, she's giving an announcement, and then you're giving this inductive reasoning and then saying, okay, on 100th day, all of them will leave. The same information was known previously also, right? Then why didn't everyone realize that their own eye color is green?
Okay, I think if this announcement was not made, then suppose there are 100 men and only one of them had green eyes, then
Okay.
then everybody means nobody can know that whose green eyes is, means the person who has green
Yes.
eyes can never know.
Okay. In that case, it makes a difference. When there is only one green-eyed guy, the fact that the announcement actually makes a difference. Right, to the green-eyed guy, he can clearly see no one is green-eyed, but she told that there is at least one green-eyed. So in that case, it makes a difference. But when there are all green eyes, how does it make a difference? Because everyone can already see 99 green eyes. So your explanation works when there is one green eye, right? 0 to 1 makes a difference, but what is the difference
It is
here?
to point out that they don't know that they have that. It is to point out that think that you can leave. She's trying to say that you can leave. One of you can leave, is what she's trying to say. One of you should leave, I think. Kind of like that.
No, okay, think about it. It's yeah, it's kind of not very simple, but it's kind of very, a lot of layers of logic is there in it. Almost 99 layers of logic difference is there. Yeah, you can try and figure it out. So yeah, this thing, it's so the concept behind this is called common knowledge. So what is common knowledge? I know that I know something. It is basic level 1 kind of knowledge, say, and there is another guy. So because he is as intelligent as I am, I can say I know that he knows the information. So knowing of knowing, it's okay. Say level 2 kind of information. And yeah, and you know that he's as intelligent as you. So he also knows that you knows the information. So you know that he knows that you know the information. So it's some sort of level 3 kind of logic. So it goes on upon how much your brain can handle. So yeah, so everyone knows all these layers of logic. So it's called common knowledge, knowing of knowing. So the answer depends on something like that. Anyway, you can think about it. So yeah, those who have seen the video, this question is not there. You don't know, he doesn't pose this question. So you have to think about this. So yeah, that you can think about. And so there is this another puzzle. It's also very, very famous. Many of you might already know. But the point I'll be extending, trying to you know, impart something else. So yeah, so the puzzle goes like this. So you're in a flat land. So flat land is a two-dimensional world, and there are 3 houses. So don't ask how the doors look like if it's two-dimensional. Yeah, just assume it's 3 houses and 3 resources. So there are 3 tanks, or yeah, 3 resources. So this provides water. This provides gas or fire. This provides electricity, right? And you have to provide each of them to everyone by forming a pipe, or yeah, it's a simple connection. So but the catch is, since it's two-dimensional, they cannot exist to crossing pipes, right? In 3 dimension you can go over it, but in 2 dimension you cannot avoid it. So there cannot exist two intersecting pipes in 2 dimension. Yeah, so is it possible? Can you supply all 3 resources to 3 houses? Can you give a connection that provides everything to all of them?
No, it's like mathematically not possible to connect.
You can do it by transferring from one house to another, right? Is it possible?
What?
I mean, I gave water to one house, and then from the one house I transfer water to other house without making any other connection from water to the second house. Is it possible?
Yeah, okay, that you're asking. So if in that, okay, if you're asking that kind of question, then I'll say I'll give all of them to one house and connect this one house to the other 2 houses. That'll basically solve the question, right? I mean, if you're allowing that kind of connection, but no, yeah. So yeah, if that is allowed, then it's fine. That's, maybe you can say that's kind of a solution to this problem. But no, that's not allowed. All of these are enemies, so they don't want to share anything, right? They don't like each other. So
We
that is
can't
not allowed.
supply all 3.
We can, I think.
Yeah,
I
yeah.
think-
Hello,
Maybe,
I think I got
maybe you can.
like a yes, like a butterfly means a shape like from water. First I
Yeah.
will join the straight. Yes.
Straight to second one or
Straight
first
to
one?
head one, and then fire like behind the water and to the house. Yes,
Okay.
and
Yeah. Yeah,
and
like
Probably behind is not possible, right?
No, it's fine. It's
yeah.
fine. You can go like this. You can go like this. Yeah.
okay,
And then
and
Then it's
then
possible.
First of all,
okay, so
let me tell
then
you.
okay, first let me draw.
okay. Maybe you can on your
You can't
write on a
supply
paper.
all 3
Write on.
houses.
No.
Irrespective
Whoever is
of-
claiming,
First of all,
they have a no. Whoever is claiming, you can draw it on a paper and show it to the
Okay.
camera. That is fine.
Okay. Wait,
Okay.
I'm
see.
drawing.
No, it's
Yeah,
not
cool.
possible to supply to all 3 houses with all 3 resources.
No. Wait. Let's see, man.
You always end up with one remaining.
Maybe it is. I will.
Then if it is not possible, then prove how it is not possible. That's also another question.
Yes. That's a good question.
It can based on the
When-
like.
See, in logic, when you say something is possible, you show it by showing it.
Yeah.
If you say something is not possible, you give an argument. Well, it's not completely true. There are existential proofs also, but yeah,
Yeah, it's
in a
like I don't remember the exact proof, but it is based on the fact that this is like a paper, two-dimensional paper, and it has all the characteristics of two. And basically, if you want to join all the houses, the shape that you end up making, it cannot exist on a surface with all the characteristic of
okay,
two.
fine. So whoever
It is
has
not
a
necessary
drawing,
to have a straight line, right?
yeah, no need a straight line. You can have curves.
Yeah.
It's fine. So is the
We
guy
can,
ready to
first
show
of
it?
all, we can
Uh,
put fire.
No, I'm
I am
trying to
Can
draw.
your
going to
line
prove
go?
that it
Can
is
your
not
line go
possible.
in between the
First of all, we
houses?
can put power and then water and then electricity.
Yeah. Can you say it again?
First of all, we put a fire on the two-dimensional paper, and then to compromise fire, we would pour water, and then we will provide electricity. It will distribute it all over three homes.
Wait.
Okay, okay. I
What is
think
this?
I have I have done the drawing actually. Yes, it is happening. I'm showing. How can I show?
Yeah. Okay.
Just do one thing. Can you post it in the? Is it possible? Let me see once. Oh, yeah. You
Let
can
it.
try to attach the picture in your this
Okay, you
chat
can
actually.
see.
Okay. Just let me.
All right. Yeah, it's visible. So can you send it back? Back, not towards. A
Means
little bit back.
means
I mean, send it away to the camera so we can see it. It's
zoom
too
out.
close.
Okay, now it's okay.
No, zoom
No,
out.
don't.
First, I would do.
No.
It's
Okay, rotate 90
earlier-
degrees.
Rotate 90 degrees and zoom.
Yeah,
out.
this should be fine. Go a little bit below. Down.
Okay.
Down. No.
Down.
I mean,
move your hands down.
Up.
yes, move your hands
Okay.
down.
Okay.
Even
No.
Do better do one
And-
thing. You can take a pic and then if you have your mobile app, you can
Yes.
take a pic and
Yes,
upload
I'm-
it in the chat.
Okay. Wait
Yeah.
a minute.
In the chat section, you can.
Arnab, I'll most probably, I think this will complete by 35, 7:35, then you
Okay.
can take.
Yeah.
So yeah, we'll
Yeah.
have time.
Okay. So I'm asking that chessboard question you have discussed. I've joined
Yeah,
late.
we'll come to that later. No, we didn't discuss.
Okay.
We didn't discuss any answers, but yeah, we just want you to show it.
Okay. Attach and send. See, you have got it.
So in the chat, so people go to the chat. So I'll open it and share it, I guess, or
Oh, actually, I missed one. Okay. Yes.
yes. So you did not provide what to what? Can you say?
Electricity to middle one. Yes. I forgot. Okay.
Yes, you did not provide electricity to middle one, right?
Okay.
So yeah,
Yes,
the
yeah.
thing is, it's not possible. You'll always miss one resource to
Okay,
one.
I think there's a means. There are total 9 curves, and there is a theory like 2 lines can separate a plane only by 4. Means there can be only 4 parts for 2 lines, 2 curves. You can separate it, and like
No. You take two.
you can separate
Okay.
a plane. Yes, you can separate a plane using 2 lines into only 4, not more than 4. And like you can use 3. If you use 3 lines, then you can at max you can divide it like 1 2 3 4 5 6 7 parts. So this goes like a pattern, like 4, then 4 plus 3 7, then 7 plus 4 11, then 11
Okay.
plus 5
Okay.
16.
So okay, whatever your argument is, I'm not sure it's correct.
Okay.
It's not clear
Yes.
what is dividing means. So
Okay.
you look at this line and some other line, they're not dividing into anything. So there's just line segments. So anyway, it turns out it's not possible. So what is this area like? What is it going at? Okay, first of all, when you're trying to solve a problem, what do? You remove houses, you remove water, gas, anything. You just converted into, nodes, points and lines, right? You abstract. So generally, when you have a problem, you try to abstract as you remove unnecessary information, right? You just, so this is the problem. 3 red points, 3 blue points. Can you join all of them to each of them on a plane, on a piece of paper, so that no two edges. So the lines joining to, okay, let's call this vertices, and the lines joining these as edges, and they need not be straight lines, they can be curvy, but they should not intersect. Okay, that's the abstraction of this problem. And it turns out it's not possible. Any embedding, we have at least one crossing. So this whole area, so first of all, this abstracting problems by, vertices and edges, it's a very general technique, and it gave to a birth to a branch of mathematics, or mathematics called graph theory. So which shortly Arnab will discuss, and that's the point. Solving problems by, just having points and edges. And the argument behind proving this, maybe we'll see later. Proper argument why it's not possible on a piece of paper. But actually we are wrong. I did say it is a two-dimensional world, but it need not be a piece of paper, right? Why are you doing it on a piece of paper? I will show a two-dimensional world in which it's possible. Can you, does anyone know the solution, what I'm trying to do? There are many two-dimensional worlds. The surface of my body is a two-dimensional world, right? It's two-dimensional. The surface of a sphere is a two-dimensional world. A piece of paper is a two-dimensional world. There are many of them. The surface of a torus is a two-dimensional world. It turns out the same puzzle, if you try to solve on a coffee mug, it's possible. You see, you can give a, you can bypass through the handle, and you can pass one into like this, so that these two won't cross. You see the beauty, right? Like that one crossing edge, you can take it through the handle, and then the other you can pass into the handle.
It's similar to providing one of things from above.
In a way, but but still you're in a two-dimensional world, and the whole is kind of providing you okay, this imagination might give you that, but if I draw it on torus, there is no up and down. But the thing is, the topology of your surface actually decides whether you can do this sort of thing or not. So it's a whole new, it's a big area called planarity in graph theory, and it's pretty deep. So I'm just trying to show it to you. So the thing is, again, a coffee mug is equivalent to a torus with here. We're just using the one hole that it has, right? It doesn't matter that it's a coffee mug or a bucket. So even if it is a bucket, then it's still the same. So that is another area called topology. They deal with objects and surfaces, how many holes they have and stuff like that. So the final homework puzzle, you can just write. So I think again, many of you might know this again. How many of you know this? Okay, anyway, I'll explain the puzzle. So there are 12 identical looking balls with you, and one of them is faulty. And by faulty, it could mean it could be heavier or lighter. We don't know that also. And in just 3 weighings. So by weighing, I mean Libya balance. No digital balance. You can just put some items here and some items here, and it will show whether which side is more or if they are equal. Only that less than, greater than, or equal to. You only can get that much information from the balance. So to find the faulty ball and also the fault, by fault I mean whether it's lighter or heavier in 3 weighings. So that is a puzzle.
But will it not be like 6-6, then 3-3, and then you know it in the next one? After
Yeah. Okay. First question: if you balance 6-6, it will anyway be imbalanced, right? You know that it will be anyway imbalanced, so you do not get any information actually.
No,
Yeah.
but
Right.
if we do 6-6 and one is faulty, so one
Yeah.
side will.
But
Oh,
you
okay.
don't know
Okay.
whether it is
Yeah.
heavy or light, right?
Yeah. We don't know if the lower one has a heavier ball or the upper one has a lighter ball. It could be anything, right?
We can divide in 3 groups of 4, and then take any 2 of those 4 and then weigh them.
Yeah, and then a lot of possibilities are there. They are imbalanced or they are equal, and then
No,
yeah, maybe.
like, hello.
Yeah, hello.
Yes, we can suppose we get a 8 and 4. From those 8, we'll put 4 and 4 on both the sides. If the imbalanced ball is is among those 8, then
I'm not able to hear. Am I audible first of all?
Yes, sir.
Yes,
Yeah,
you're audible.
whoever is telling, I'm not able to hear. I assume. Anyway, this homework, so yeah, please, yeah, don't tell any solutions. But yeah, it's not very easy, but I think
We
some
can
of you
use
will
binary
get it.
bits. Is
Yeah,
it
you can
correct?
try. Yeah, you can try whatever you want. So whatever
Yeah,
solution you get, ask it
I
to
got
yourself.
it.
Right.
Can
Okay.
I'll keep it to myself. Okay.
Yeah, I'm sure it won't be correct, so you can tell it. Fine, no problem.
Okay. So we take. I took 6 balls and I weighed them 3 by 3.
Okay.
Yeah. Then I
So
took
let's say you
3
get
of
equal.
the.
Let's say you get equal.
Let's say if I get equal, I take the next 6 balls and I take out any 3 of the other 6 out of the I take 3.
Okay.
Imbalance.
Yeah. Then I take the out of the 6, I take out 3. Then I take another set of 3 from the balanced one.
Yeah. Okay. Yeah.
So I can know that if this 3 has equal or faulty one, then
Yeah.
I
Let's
have
say you
only.
got again equal. Let's say you
Oh
got again
no.
equal.
Yeah. It's wrong.
Yeah.
It's wrong. Yeah.
Yeah. Right. Okay. Fine. It's wrong. So yeah, you can try it. It's not so easy, but yeah, if you manage to solve that, then I have even harder problem. You have 13 balls again.
that will just last time. We will divide those 12 balls in group of 8 and 4. Okay.
Okay.
Then we will take those 8 ball and put 4 on the one side and 4 on the other side. If the faulty ball is in that lot, then one of those.
First of all, let's say they're equal.
Okay, if they're equal, then we'll go for the next 4. Then among those next 4, we'll divide them in 2 and 2.
Okay.
Now, obviously, the faulty ball is there, so we will know that either among these 2 the faulty ball is, or among those 2.
How?
Because first we had 12 balls. First we took 8 of them, divided them into 4 and 4, and they got equal. They both were equal. So now we know the faulty ball is among those 4, the remaining 4.
Yes. But when you divide into 2 and 2, which of them has a fault? How do you know?
We have done only one measurement, right?
Yeah. Second measurement, how do you do?
Second measurement, we have 2 and 2. For the second measurement, we take those 4 balls, divide them in 2 and 2. Now we know among which 2 is the faulty ball. The third measurement, we put those 2 balls in opposite slots. So we will know in which one it is.
No, I'm not sure what you told is correct. So okay.
We don't know whether it's
Okay,
heavier
let
or
me.
lighter.
Can I say what if the 8 balls which you are taking and they turn out to be of different weight? Then
yes.
Yeah, this is the hard case actually. Yeah.
Yes. No problem.
For the case of if the first 8 are equal, like for the next
unequal.
What if first if 8 are not equal?
Yes.
No.
In
Yeah,
the
yeah.
first,
Maybe
when
this is the right direction, so you can try it. You can try it, and then if you get it, then try for 13 balls. And yeah, it's 7:35. So as I promised, Arnab, we can start. Maybe we can discuss at the end. Okay, after
Like we
Arnab
can
is finished, then
swing up the next 4.
no. When Arnab is finished, we can again come back to this. Okay. Okay. So yeah, Arnab, start with the.
Just one second. Yeah.
So we'll definitely come back and maybe discuss previous puzzles also. But yeah, after this is over.
Yeah, just one second. Sorry. Okay. So I hope I'm audible, right? Just one second. I'm
Yeah,
audible.
yeah.
Like,
Yes.
Yes.
Okay. Okay. So till now, Madhu, he gave like a sort of informal introduction in a way to graph theory. So it's always like whenever we are going through any topic, it's always better that we have a formal introduction. So for now, like, okay, this will be a sort of formal introduction to graph theory, which is quite simple. So let's begin it. Is there any problem in the font size, or otherwise I can increase it?
Better
Can you-
zoom it. Yeah, zoom it.
Okay.
More. Yeah, this is fine. Yeah.
Okay. Oh, sorry.
Yeah.
Okay. So just I'm facing one problem because it's not going to next slide automatically. Is there any method to take to next slide directly? Space.
Try space. Yeah, space.
Space is zooming it.
Down. What is down doing?
Down is like this.
Yeah. Just okay. You open it in PDF, na? So
PDF also I'm facing the same issue actually. Just one second. Well, I'll open the original PDF. There I'll take it. It will be better.
yeah.
Yeah, that will be better. Okay. Yeah. So okay. So let's go through the formal definition. Okay. So you can consider graph as a triple actually. Okay, sorry. Okay, you can forget about this thing actually. Okay, just let us start with okay. So graph you can consider as a collection of some vertices and some edges. For now, you can forget this part. So vertices, like you can say it is like V1, V2, V3, V4. And the edges, like it is some set which is different from V. You can say E1, E2, E3, E4, and so on. And what this some special symbol I you can say. So it says like some kind of incidence relation. So I'll tell what is that. So okay, let me take help of his diagram. It will be more clearer. Okay, so basically a graph will be some collection of vertices. Vertices means you can imagine in terms of a pictorial diagram. So these black dots which you are seeing here and here, you can consider them as vertices. Okay, so V1 is this black dot, V2 is this black dot, V3 is this black dot, and V4 is this black dot. Okay. Now, what edges are? You can consider the edges as some lines which connect the vertices. Okay. So the edge which connects V1 and V2 is E1. Okay. And the edge which connects V1 and V4 is E4. Okay. And so on actually. So what this incidence relation or I, what it says that this E1 is connecting V2 and V1. You can see it from here actually. You have this pair here, and the way is another pair, yeah, here. So basically, as you can see, an edge will have two endpoints. Like in normal geometry stuff also, you would have seen this type of stuff. So basically, you can forget about this type of stuff. Like as formally, I'll say it again. So basically, a graph is a collection of some vertices and edges. So the function of, like the work of edges is to connect two vertices by a line, you can say. Imagine in this fashion. Okay. So there can be more than one edge between two vertices. As you can see here, V1 and V3, there are two edges, E5 and E6. And there can be an edge to itself. So this E7 has is an edge from V4 to V4 only. Okay, so this is called a loop. So I hope the basic idea of graph is clear till now. So this is sort of called a graph. So Madhu previously he explained that planarity problem. So that is he abstracted later into a graph. So this is what a graph is in a way. Okay, the more formal definition is this. So I'm not going that much deep, but this is sort of enough for our work. So as I told, these are called loops, like edge from the same vertex to same vertex. Yeah. And generally when we talk about graph, we talk about simple graphs. It means that between like any two edges, between any two vertices, we don't have more than one edge. Like here we had more than one edge. So these type of graphs are not called simple. Okay. But between any two vertices, if there is at most one edge, then we call it a simple graph. So from now on, we are going to consider this type of graphs for now. So does anyone has any queries like regarding the definition? If you have, please ask it, because the definition is more important regarding the graph. So if it's clear, can someone tell it's fine so that I can proceed?
Is it possible that if a edge can go through three vertices, or
no, edges between two vertices. What you are saying is called hyperedge. Okay, hyperedge can cover more than two edges, two vertices. But for now, by edge we mean they are connecting only two vertices.
So edge is a subset of V cross V.
Yeah, in a way.
Connecting, yeah.
Yeah.
So only two. Yeah. As Arnab told,
yeah.
if you are having more, like something is a collection of more vertices, it's called hyperedge. Yeah.
Yeah. So for now, whenever we say edge, we mean this only. No, not of the type which you are telling. So is it fine? I'll proceed then to the next slide.
The edge between B1 and B2 and V3 and V4 are parallel. Then why they are said this is a simple?
No, by parallel, we don't mean that direction wise parallel. By parallel, we mean that they are edges between same two vertices. See, V1 and V3, these are edges between the same connecting same vertices actually. So we say them to be parallel. Don't see direction. These two
parallel
edges,
is not geometric parallel. You know, yeah, there are parallel in this diagram, but that's not the parallel. You can draw it in a different way, right?
So edges here are straight lines.
No, your voice.
Edges here are not straight lines, right?
No, like for pictorial representation, I'm just showing it as straight line. It can be a curved line and all. It should just connect V2 to V1. And more formal definition is that more formal definition is what Madhusudan told. Like it is a subset of, like it is okay. Let me draw and show it.
Okay. First of all, show the diagram, Arnab, once. One point. So think of this graph as a friendship relationship. So there are four people, and if there is an edge, it means that they both are friends. Okay, and if there is no edge, that means there are strangers. They don't know each other. Okay, so however you draw, it's just a drawing, right? I can put V2 somewhere else, but the connection is the same. the information of friendship between people, that is the graph. Okay, it's not how you draw it. Okay, so I think you got what I'm saying.
Yes.
It's the way those
Yeah.
things are connected. Assume there are nodes and beads and they're connected with threads. So however you put it, it doesn't matter. It's the same object. Yeah.
Yeah.
I think you can.
And yeah, just for the sake of completion, okay, so I'll just mathematically I forgot to show the notation. So if this is V and this is U, vertex V and vertex U, and there is an edge between them, then we show like we depict it by like two set actually like this. So basically edge is a set of two elements. Okay, so you can consider where the elements are like edge is a set of two elements and the elements are part of the vertex set. So that is what we mean. So so this is a mathematical definition. So this is an edge where V comma U, they belong to this vertex set. So vertex set is nothing but the set of vertices. So this is actually the formal definition of an edge. So to it's always convenient if we deal with figures. So whenever we are dealing with figures, we make circles to denote the vertices, and if there is an edge, like if this is part of our edge set, like we consider, like we have some set, such collection of sets are called edge set. So if this is part of our edge set, then we say then we pictorially we add this line between them. It can be a curved line, it can be a straight line, but like pictorially we want to represent some kind of connection. And as Madhu was telling, it's kind of friendship and all. Okay, and this V and E together they form a graph. Okay. This V and E, set of vertices and set of edges, together they define a graph. So which is of this type. So this is set of vertices and these are set of edges, then together they form a graph. So this is sort of a formal introduction, like formal definition of graph actually. So I hope it's clear. So I'll be going to the next slide. Yeah. Yeah. So as I was telling, it can be described as a two element subsets. I like this. So V1, V2, the edge between V1, V2 is this thing. The edge between V2 and V3 is this thing. And so on. Okay, as I explained. Yeah. Yeah, so some trivial graph terminologies. So if a graph has no vertices and we call it as empty. And if a graph doesn't have any edges, then we call it as trivial. Yeah, these all I think we can skip. Okay. Okay, so it's very important actually. Oh, sorry, I'll show it using here. So, okay. So, if there is an edge between two vertices, then we say that they are neighbor of each other. Okay, so here V is a neighbor of U and U is a neighbor of V. So this is what we mean. Like if they have a connection, then we say they are neighbor. So that is one small terminology. Or we can say they are adjacent. So same stuff. Yeah, this thing, yeah, fine. Yeah, so this is very much important actually. We'll see for only simple graphs. Okay, so so this is say a vertex. Okay, and some edges are connecting it to some different vertices actually here. Okay, so we define a so if this is a vertex V, then we introduce a terminology called degree. Okay, in short, we denote it as D of V, degree. So degree is nothing but number of edges which are connected to this vertex actually. So can someone tell what is the degree of this vertex V?
4.
Yeah, so then you got it. Yeah, so you got it. What degree is? Yeah. So this was sort of a formal introduction. This I think won't be needed, but just for the sake of completeness, I'll tell. Okay, so the set of neighbors of V other than V itself is denoted by this set actually, N of V. So for now, for today's session, you won't be needing this definition, but this definition you will be needing it. Okay. I'll go to one different slide. Okay, sorry. Yeah. Okay. So we'll go to some new topics. Like till now, like even in the last discussion also, we sort of discussed this stuff. Just for the sake of completeness, I revisited them. So now let's have a look at this particular thing. Okay. So we defined something called walk, trail, and path. Okay. So okay, so first mathematically, formally I'll tell what walk is. Then using this picture again, I'll explain it. So walk, you can say, is an alternate sequence of vertices and edges. Okay, so V1, then E1, then V2, then it's basically it's an alternate sequence of vertices and edges, with one condition being that this edge E1 should connect V1 and V2. So the edges which we are mentioning between two vertices, those two vertices should be connected by that particular edge. Okay. So let me explain it using this diagram. So what is a walk? Like you can say, like physically, you can consider it as you are walking on the graph. So you start from here. So you go to V2 via this edge E1. Then you go to V5 via this edge E4. Then you again come back to V2 via this edge E4. Then you go to V3 via this edge E6. So basically you got an intuitive idea what I mean by walk. Like you start walking. Basically you start walking, and whenever you walk, you start listing the vertices and the edges which you traverse through actually. So when you start start at V1, then V1 gets written here. Then when you go through this edge, then E1 gets written here. Then you reach V2, then V2 gets written there. And then you continue like this. And the sequence which you generate, we call it as walk. So does anyone has any like confusion still regarding the definition of walk? If it's fine, then I'll go to this particular definition, trail. The only difference
one
between
thing.
Yeah.
So you people should have solved some puzzles like you'd have 4 points and all of them are joined to each other. You try to draw this without lifting your pen and not redrawing the same thing again, something like that, right? That analogy you can look here, like what is a walk, what is a trail, what is a path. In that way you can imagine. So walk is anything without lifting your pen. You draw like anything. You can redraw on the same thing. You can come back to the same point. It's fine.
Yeah.
So that way it's better to say, I guess. But yeah. Informally. But formally,
formally this is the definition actually. And trail is a walk, but the edges which you are traversing should be distinct. Okay, so you cannot repeat an edge. So here in walk, see, you were repeating an edge. So you went from here to here and then came back using the same edge. But in a trail, the vertices can repeat. Okay, but the edges cannot repeat. So I'll show a trail. You go from here to here, then you go from here to here, then you go from here to here, then you go from here to here, and then you go here. Okay, so you see that the vertex 2 was repeated. We are fine with it, but none of the edges was repeated. So we went like this, like this, like this, like this. So no edges were repeated. So as I mentioned, all edges are distinct. So so this is the difference between walk and trail. Okay, now this is one of the ask.
In trail, is it always possible to have a trail? Because walk is always possible because we can repeat.
Yeah.
Is trail also always possible or not?
What do you mean by trail is possible? What
No, trail. Okay, trail. Okay, so no. Okay. Do you mean that trail which covers each and every edge?
Yes.
Yeah. Okay.
So that is a question. That is a
that
famous
we have to
question.
cover everything but not repeat something.
So covering all edges is this Euler trail, I guess.
Yeah.
Yeah, that is a famous thing. Maybe we'll come back to later. Yeah,
But
we have
it's not
conditions for
always
that.
the case.
Yeah.
It need not be always possible.
Okay.
Yeah, let's give him a simple example. Take one vertex in the middle and 3 vertex around it, and this is connected to all 3 of them. So it's called a claw.
Basically draw it. Yeah, you consider this particular graph.
Yeah, this is also enough. Yeah.
Yeah, you consider
can
this
you do it
possible
here?
graph. Yeah, you cannot do it without traversing one edge backwards.
Yeah, you can only do 3 at most, actually.
Only 2 edges we can cover.
Yeah, 3 vertices I'm saying.
Yeah, 3 vertices and only 2 edges.
If we have even number of degree, then we cannot get, I mean, we will have to traverse one more to get out, I think.
No, even degree I think is possible, trail.
Yes, actually,
if every vertex.
It turns out that it's the exact condition that we need. Every vertex has to have even degree.
Yeah.
Then it is possible always.
Yeah, but this in detail we'll talk in another session, like where we go to the second half of graph, like in detail. Okay. But that's a very good question actually, with whoever asked that about this thing.
Okay.
Yeah, and last we'll come to path. So a path is a trail where none of the vertices are repeated. So basically you can say that a path is a walk where no edges are repeated and no vertices are repeated. So path, you can say like you start walking from here, you go here, then you go here, then you go here, and then you go here. So this is a path, but so this is a path, but no edges, no vertices should be repeated, and no, obviously if it is a trail, then obviously no edges are repeated. So this is a very simple definition of a path. Yeah. So basically you can imagine that once you start walking, the previous vertex you cannot visit again. Okay. So you start walking and here. So it's a path. So formal definition is it's a trail where all vertices are distinct. So path you can like sort of stretch it in a straight line. So you start from here and you can reach here. So this is a path. Okay. So so this is, I hope like path should be very simple. Okay, so this is one small table. So obviously every path is a walk and every path is a trail. Every trail is a walk, but every trail need not be a path. Okay, like this one. And obviously every walk obviously is a walk, but it need not be a trail. Obviously it need not be a path, like this one. So okay. So this one small last like formal concept before we go to some interesting problems. Okay, some of which I'll give it for your homework sort of thing. Like so basically like we say graph is connected. If we like from any vertex we can reach any other vertex by traversing, like by a walk or by a path. Like by a path we can reach any vertex. Like if you start here, you can reach here via this path. Similarly, if you are here, you can reach this vertex here. So a graph is connected if there is a path between every pair of vertex which you choose. Okay. So this is what we call as a connected graph. So basically everyone can go and reach another person. Okay. But like if that's not the case, it can happen that a graph need not be connected. Like you can think in terms of islands. Like you have houses on an island, so the houses connect the so the roads connect the houses. Okay, so we can say that the houses are connected in a way, but from one island to another island we don't have any road, so we can say that the two islands are disconnected. Okay, so in same analogy we can think in terms of graph. We can have certain portion of graph which is connected with each other, like certain subset of vertices which are connected with each other here and here, but the entire graph need not be connected. Okay, so this each part, okay, we call it as connected component. Okay, so these are, you can say it is one component of the graph and they can reach each other via some path. Okay, but from this component you cannot go to this component because there is no edge which will take you from this component to this component. So can someone tell what is the number of components here? I wrote it 3. So like, okay, I'll give some new diagram and I'll ask. Okay, if this entire, okay, sorry, if this entire thing is a graph and these are the vertices, then can someone tell what is the total number of connected components here?
4.
4.
4.
Yeah.
4.
Yeah. So I hope you got the concept. So yeah. So let's now
I don't
proceed
get
to some
it. I didn't get it.
Which one?
This component of
You didn't get the concept or this answer?
yes, I did. No, I didn't get concept. What is component?
Like component, you can say it is a like a set of vertices. And we say component is connected if we can reach from like from any vertex in that component to any other vertex in that component.
Okay, and
so basically between one component and another component you don't have a edge basically. So you can see there are 3 components here. They all are connected. Okay, by connected I mean you can start at any vertex and you can end up in any other vertex. Okay, here by traversing via these edges. Okay, but you start here and try to get here, but there is no edge which will take you here, or no path to be precise, which will take you to this vertex. So so these 3 basically form different components. And each one we call it as connected components. Is it clear or should I give more explanation?
Sir, I also did
so
like
means in this one, okay.
Yeah, tell.
In that green one,
Yeah.
so middle one can go to any of the 3 vertices. Okay, so
this one
yes.
can go to any, yeah.
So that's why answer is 3 or anything else. Means why 3, number 3?
No, see this red and this green. These 3 are 3 separate like sort of components in a way that, okay, so this complete thing is a graph. Okay.
Another very easy analogy. So think of graph as beads connected with threads. Okay. So can you hear me?
Yes, sir.
Yes.
Yeah. So this configuration of beads and threads, if you have, how many objects do you have? How many different objects do you have? Like you'll have three objects with you, right? One string, one thing with 4 items here, and another thing. Like you'll have 3 items with you, which are different.
2 beads and between them string.
Yeah, vertex is a bead, and the edge
No,
connecting them is a bead.
That
Sorry.
these
Vertex is a bead.
These all are a single graph actually.
Yes, okay.
This is a single graph. Not these are
This
not
whole
3
is-
separate graphs. Yeah, this
Okay.
whole is a one single graph.
Yeah,
Yes.
it all this thing is in a box. That is what we call it graph, and inside that we have these beads, and they're connected by strings. So by connectedness, we mean if you pick one bead and lift it up,
Okay.
all of those connected to them, all of those will come together as one piece, right?
Yes. So there are three different
Yes,
pieces.
exactly.
Okay.
So each piece is called a connected component. So we have 3 pieces here.
Okay.
Right.
Okay. Now I get the answer 4. Okay.
Yeah. No, answer is 3 here. Here it's 3.
Here and in that case it was 4.
Yeah.
Yes. Yes, I got it now.
Okay.
Yeah.
So here you have
Thanks, Madhu.
2 identical, say isolated.
Yeah.
Okay,
Yeah.
fine.
And this was one last. Okay, so so sorry. So we just one final definition I forgot to tell. So we said that in a like the path is a trail where all the vertices are distinct. Suppose we consider a trail where except the first and the last, rest all are distinct. Okay, like you have V1, V2, V4, V5, then again V1. Then that thing we say it is a cycle actually. So in a way, okay, no, in this figure it should be this thing actually. In this figure it should be V2, V4, V5, V3, V2. So you can see this is a cycle. So it is a closed path, we can say, like it's a closed path. So it or in a way it's called cycle. So it's a basically you in your sequence every vertex is distinct except the first and last vertices. So V2, V4, V5, V3, V2. So this is a cycle. So I hope this definition is clear. And if a cycle has only 3 like vertices like this, if it has only 3 vertices, then we say it is a triangle. Okay, in a way. And other than that, if it has more than 3 vertices, then we say it is a cycle. So it has
Excuse me.
Yeah.
In the previous example that you were saying.
Which one? This one?
Yeah. So if we have one more vertex above V1.
Here. V1,
and we make one more square like this. And then.
Yeah, one more square. Okay, here like this.
Then if we start from V2, V4, V5, V3, V2, and then V1, V6, V4, V2. Is that also a cycle?
No, it's not a cycle because I told except the first and the last vertex, the middle one should be distinct. But in your case, the middle one gets there's a repetition in the middle.
No, middle one comes. Okay, actually V4 comes twice. V4 comes twice. That also happens, right?
Yeah.
So that there also it's wrong.
Yeah. Instead, if you say this was a V6 here and it was connected like this, then V1, V2, V3, V5, V4, V6, and V1 will be a cycle.
Okay.
Yeah. So basically, you start traversing, and when you traverse, you should not repeat any edge. You should not repeat any vertex, and then again you should come back to the starting vertex. So that thing which you do, it is a cycle basically. So that's a basic like intuitive idea which I gave you. So let me just take you down here. So basically cycle is like you continue like this. Okay. You keep traversing and then at the end you return. So you can say it's sort of a closed thing. So we call it a cycle. Okay. So difference between cycle and a path is path begins from a new vertex and it ends in a new vertex, but cycle will end at the starting vertex. So that's the basic difference. So this becomes a path, and when you like after reaching here, if you come back here, then this becomes a cycle. So I hope the basic idea is clear. Okay. Okay, so now let's proceed towards some interesting problems. Okay.
Even if you don't get it first time, it's just terminology, because it's just the language. So yeah, don't worry much.
Yeah, if you give a slow, like like these are all new concepts, right? So if you give a slow read after this session, then I hope you'll easily get by just reading the slides. I'll upload the slides. Okay, so now we'll do some basic problems actually, which like it's all 12th class concept level. No need of any new concepts. Like the terminology we introduced just because the problems will be familiar. Yeah. So can someone prove this thing? Like it's very easy actually. Use pigeonhole, like in a way. In any graph, there exist two vertices of same degree. Can someone prove it?
So
in a simple graph.
I'll pose the same question in an informal way again. So just to show parallel between real world problem and graph theory problem. So there is a party and people do some handshaking. So prove that there exist two people who shake the same number of hands. So it's the same. So that and this problem are actually same, right?
Can someone mute if they're not speaking?
So am I audible what I've told?
Yes.
Yes.
Yeah, that and this problem are same.
So we can assume that each edge has different, each vertex has different degree, but the degree can vary from 1 to n minus 1. But there are n edges and vertices.
Degree can be 0 also. Like there can be totally isolated vertex, like here. Like you see, where is that figure? See here, this vertex has degree 0.
Okay, we can ignore all the vertices which have degree 0. And we can deal with the components which do not have a degree 0. Oh, no, then it won't. I mean,
you're quite close. Think carefully.
If there are two components of degree 0, then we are done. Okay. But if there is only one component of degree 0, then we will ignore that component. And then we will apply the reasoning that there are, certain number of vertices, and the edges is always n minus 1. So one edge must have equal number of degree.
You mean vertex, right?
Sorry, I just mixed up the terms. Sorry.
Yeah. So in a more okay, so your argument, I'll make it more formal in a way. But more clearer actually. So basically, okay. So this I hope everyone will agree. Like the possible degree of the vertices are 0 to n minus 1. Okay. But can someone tell me whether 0 and n minus 1 both, whether it will be there together in the sequence or not? Like if we yeah,
it will not be there together.
Yeah.
We need
Yeah,
n
it
plus
won't
1
be there.
vertices
Either
for that.
0 will be there. No.
No, if 0 is there, then n minus 1 is not.
See, suppose you. Yeah, if 0 is there, then n minus 1 is. See, if you have n vertices, then can you have it 2 vertices such that one of the vertex has degree 0 and another one has degree n minus 1? So it's not
No.
possible.
No.
Yeah. N minus 1, it means that. So I hope you got the fair idea. So.
Oh yes.
Either you got the idea, right?
Yeah, because there are n possible ways, 0 to n minus 1, and then if 0 is there, n minus 1 is not there. So we only have n minus 1 options. So one will repeat. That was the logic, I think.
So yeah, so that was the logic. So did everyone get the idea like how to approach this problem, or is there someone who didn't get the intuition behind this problem?
Can you please repeat if you don't mind? Like, didn't understand it.
Yeah. So ask you only. So can you, if we have n vertices, then what are the possible degrees of the in a graph?
Yeah, like 0 and n minus 1 won't exist together. Okay, that is okay. But then with that.
Yeah. So so basically in a graph, the number of possible degrees, like total number of possible degrees is n minus 1, like total number of possible degrees. Okay. Different. You agree?
Hello?
Yeah.
Sir, I think your voice is lagging, or maybe it's my.
Okay, fine. So as you're saying, there are n minus 1 possible degrees and n vertices. So there are n minus 1 boxes and n people have to pick from n minus 1 boxes. So 2 people have to pick from the same box, right?
Oh yeah, get it. Okay, yeah.
That is a Pigeonhole principle. So those 2 vertices will have the same degree.
Yeah, I'm audible right now.
Yeah.
Okay, sorry. Yeah. So okay. So if I'm not audible, please let me know. Yeah. So this is I'm audible, right?
Yes.
Yeah. Okay. So this is one of the famous equality, which is called Euler's equality. Okay. So what it says is that if we have m number of edges, okay, like the total number of edges in the graph, like this is a simple graph, okay. So if the total number of edges is m, okay, then the sum of degrees of the vertices is 2m. Okay. So can someone try to prove this? Like it's simple. Can someone from the audience try to prove this thing? First of all, the question is clear, right?
Because it will be from both the vertices, so it will be twice of m.
Yeah. So basically, every edge will contribute to the sum in a 2 ways. Sorry. So if this is an edge, so this edge will be counted as 1 for this particular vertex's degree, and again it will counted as 1 for this vertex's degree. So basically, in that sum, each edge will be contributing 2. Okay. So if you add all the edges, then it will get 2m. So this is sort of a very simple argument. So did everyone get the argument? Like whoever gave the answer. So
yes.
Did everyone understand his argument?
Yes.
Okay. Yeah. So okay. I forgot to change the number. Okay. So take screenshot of this problem, and this sort of a homework puzzle for you. I'll upload the slides again, but in case you forget like which problem you have to solve, try this thing. Okay. Try this problem. It's like, again, I guess it involves pigeonhole principle only. Try this problem. I will discuss in the next session. So I hope you took this screenshot. If not, it's not an issue. I'll later upload this slide anyway. Yeah.
G is connected means that G is one component.
Yeah, G is one component.
Okay. Again, the informal variant. So we have n number of beads, and beads are connected with strings. Now it's giving that every bead has strings with at least n minus 1 by 2, meaning at least half of the remaining beads. Then prove that if you pick up this one, all of them will come up. Basically, that's the question.
In case you like, yeah, you're audible.
In previous question, I have one doubt. I didn't understand the two part. You said it will be contributing.
Okay, so how? Okay, you tell me, how do we calculate the degree of a vertex? Like what you do? Like you see how many edges are like basically are attached to that vertex, basically, right?
Yes.
Yeah. So that particular edge is attached to two vertices. Okay.
Yes.
So both of them, when they're counting degree, it will count this vertex, this edge's contribution in it. Okay.
Yes.
You got it, right? Okay.
Yeah.
Yeah. So yeah, so this is the problem which I give for like your homework. So this is the last thing which we'll discuss before we sort of like, whoever is interested or whoever came up with a solution of last week's puzzle, we can have a brief discussion of it. Okay. So this is a very famous theorem, like easy to prove, easy to understand also. So if a graph on n vertices contains more than n by 4 edges, then G contains a triangle. Okay. So what do I mean?
N square by 4. You told n by 4.
Yeah. Oh, okay. Sorry. N square by 4. Okay. So if you have a graph G which has n vertices, and it has more than, note this, more than, okay, not more than or equal to, it's more than n square by 4 edges, then G contains a triangle. So what I mean by G contains a triangle, it means that the graph has 3 vertices such that they are connected in this fashion. It has 3 vertices which are connected in this fashion. Okay. So this is what we mean by the graph has a triangle. So if you just draw an arbitrary graph here like this, and this is our graph. So we say that this graph has a triangle because these 3 vertices. Yeah.
Do we prove this by AMGM? Because number of edges will be n into n plus 1 by 2.
One of the methods is AMGM. I'm not discussing that method, but yeah, that's one more method, at least what I know of. You can try it in your free time, like exactly how you proceed towards solving that. I'll be discussing in 2 ways. One I'll give for you, like sort of homework again, and one I'll discuss it now. Yeah, but that is also one of the method which you're telling, AMGM. But I'll use Kochi. Yeah.
In this question, parallel edges are allowed.
No, not allowed. Okay, so I forgot to tell, when we just tell graph G, it means that it's a simple graph. Okay, means no parallel edges, no loops, nothing. If there are parallel edges and if there are loops, then it will be mentioned explicitly. Okay, that's the terminology of graph problems. Okay. Yeah.
Okay.
Yeah, that's a good query. Yeah, thanks for asking. Yeah. So we'll go over the proof. So we'll do proof by contradiction. Okay. Okay. So some parts I'll ask you guys only to sort of explain it to me. So okay. So when we have suppose we have let the number of edges be m. Okay. And let it be more than n square by 4. And assume that G doesn't have any triangle. Okay. So basically it means that no two adjacent vertices have a common neighbor. Because if two adjacent vertices have a common neighbor, it means they form a triangle. Okay. So the sum of degree of x plus sum of degree of y is less than equal to n. So can someone tell me why this holds true? The sum of degree of x plus sum of degree of y is less than n. Less than or equal to n. Why it can't be n plus 1, n plus 2 and so on. Like assuming that there is no triangle in the graph. So if you take, if you take an edge, for an edge I mean. If you take an edge, which is this xy, and you sum the degree of the vertices there, then it is at most n. So can someone tell me why this is the case?
Because if we take
Could be connected in a circle.
Yeah.
Because in extreme case, if we take that one of the vertices is connected to all, then none of the other vertices will be allowed to be connected to the other one. So in extreme cases, it will be like n-1 or something like that.
No, I want the formal argument. Like that is one particular case you're talking about, but I want the formal argument why this is the case every time. Like what will happen if it is more than n?
If we take just like n into two parts and take two vertices, extract from them, so n-2 and let n to be an even integer, even number. So and the n-2 can be divided into two parts. So in n-2 ways, n-2 half of n-2, the one will get attached to the half of n-2 vertices, and the other vertex will get attached to the half of n-2 vertices. So if we add them, and then also the common relationship between them, the two extracted vertices, then the sum will come out to be equals to n.
Okay, so let me. Okay, so how do I put it? Okay. No, what you are saying is it's connected in that way or that way. I want a formal argument. Better I'll give it like this. How formal argument works actually. So let me take you here. Okay. So this is. So this is my x. Okay. This is my y. Okay. So how many vertices will be left here? n-2. Okay. And I have some edges going out from here. Okay. So basically these edges are getting are going to different vertices. Okay, here. Okay, so from one single vertex, we are not, like as I told, there is only at most one edge from this to any other vertex. Okay, same from this. Okay. So we are so basically in a way we are counting the number of edges other than this particular thing. We are counting the number of edges which are going there. So if dx plus that dy quantity, suppose it's greater than n, okay, then this one edge is contributing here and is contributing here. Okay, so you remove that thing. So you bring this to this side. So it means that the sum of edges here and here, it is at least is strictly greater than n-2. Okay, strictly greater than n-2. But the total number of edges is n-2. Okay, sorry, total number of remaining vertices is n-2. But from this both, from x and y, the number of edges which are going towards them is greater than n minus 2. So by pigeonhole principle, it means that there is one vertex which is receiving edges from both x and both y. Okay, so this is due to pigeonhole principle. But I told that there is no triangle, but this is clearly a triangle. This, it's forming a triangle. So that's why it's wrong. It was wrong to assume that degree of x plus degree of y is greater than n. So degree of x plus degree of y is at most n. So this is the formal argument. So this is how you should be giving formal arguments actually. So what you were trying to give was some kind of informal argument, catching one particular case and then trying to give, but this is how we proceed actually, trying to give formal arguments. So I hope,
so this works for every x and y, na?
For every
graph.
x and y, for every x and y which are,
If they are
like connected by an edge. Yeah, if they are connected by an edge. Yeah.
Okay. So for if so there could be a question means in further proof that it might there be no edges between x and y.
Yeah, there might not. In that we are not bothered about that case. We are only bothered about this particular case.
Okay then.
Yeah. And then what we do, we can do this kind of manipulation actually. Sum of this is degree whole square. Okay. Sum of degree whole square summation. You can. It's a very simple algebraic manipulation. These both are same. If you observe carefully, these both are same thing, which we are writing it in a, like we are expanding it and writing it in this fashion. Okay. So you can, like, it's very simple to observe. Just algebraically you expand, you will get this thing only. So I'm not going over the expansion. So when you do this expansion and using this inequality,
Hello, your voice is cutting.
Yes.
No voice. You are not audible.
Hello? Am I audible now?
Yes,
Hello?
yes. Now you're
audible.
Yeah. So yeah, whenever my voice gets cut, please do tell me. Yeah. So as I was saying, this simple algebraic expansion, basic algebra, which you did in school, like a plus b whole square type only. And this particular thing gets upper bounded by m times n.
not audible.
Okay. The number of edges is m.
Now audible.
Madhu?
Yeah.
Am I, like, is my voice getting cut?
Yeah. I think you can just move to next slide.
Yeah.
Spending too much time on that. Already we have to wrap up, I guess. Move to the next slide. Anyway, people know Cauchy squares, right?
Yeah. And is there any delay? Am I audible?
Yeah, but it's kind of cutting.
Oh, but the slide is visible, right?
Yes. So
yeah.
Okay. Maybe
okay, you tell it.
Yeah. Fine.
You come.
Yeah. So as you can see, this sigma dx square, you can use Cauchy squares to show that it's at least 4m square by n. So do you know Cauchy squares inequality? How many of you know? How many of you don't know? Cauchy's quartz.
Don't know.
Yeah, that maybe we can. Actually, this you can prove easily also, but we don't really have time now. But yeah, we have a inequality of sum of squares with respect square. Sum of squares is at least the average of square of sum. This we have. Right, so this previous result, if you use that sigma sum of degrees is at least is equal to 2m, then we get it's greater than 4m square by n. And we know that this is less than mn. So if we cancel out m, we'll get that m is less than or equal to n square by 4, contradicting our presumption. So it's yeah, a little bit technical for you. It's very basic for us, but yeah. Anyway, yeah, maybe.
What is what usually we hope.
Yes, it's cutting again.
Okay, I'll just type it. Just 1 second.
Anyway, I think we can. Okay. If you guys want to discuss something, you ask. But I think the session is. You can get the slides later.
This alternate proof is a homework again. Like I'll see this hint and then try to prove this using pigeonhole principle. It will be a simple proof.
Yeah, so that's it, and thank you for bearing for. I mean, it's supposed to be 1 hour, and then I guess it went to 1.5 hours. But yeah, so anything else you guys want to discuss, or maybe we can do it in the next session. If you have something
previous questions, I was very curious about that chessboard one. I have spent a lot of time in that, but I didn't get any answer.